Thanks for the intro, Adrian, and thank you all for waking up for this talk. My name is Grant, and I'm a PhD student at UC Berkeley. I'm advised by Vern, Paxson, and David Wagner. And today I'm going to present some work that I did with both my advisors, as well as other terrific colleagues at UC Berkeley and the Lawrence Berkeley National Lab. And our work is going to focus on how we can protect enterprise users against credential spearphishing attacks. Now, I'm sure what many of you know what spearphishing attacks are, but just so we're on the same page, we're looking at attacks where the attacker is going to craft a targeted email that's designed to trick a victim or victims at an organization into giving the attacker some sort of privileged capability. So that might be tricking the victim into installing malware on the enterprise's network or revealing their credentials, for example. Now, over the past couple of years, we've seen spearphishing attacks used to devastating effect, breaching numerous corporations, organizations, even government systems like the White House, and more recently, political organizations and figures like the DNC and John Podesta. And it's really a growing and prominent threat, sort of as we've seen lots of modern technical defenses advance with automatic updates and hardened browsers. It's really become easier and more effective for attackers to target and attack humans rather than machines. And so into this sort of open and unsolved space comes our work, where we're going to focus on a particular genre of spearphishing attacks, where the adversary is going after enterprise users, and they're aiming to steal the user's credentials. Now, we focus on credentials for a number of reasons. But really, nowadays, credentials are sort of this gateway to a vast sort of array of resources for an adversary. Right? Sysadmins are hunted routinely by organizations like the NSA and their foreign counterparts, and sysadmin credentials are sort of the gateway to everything in the enterprise. But even for an ordinary user, things like remote desktop and VPN usage provide sort of a tunnel into the network systems. And even if they don't have that access, right, we saw in the past election that you can weaponize or sort of steal emails and documents to a devastating effect. Right? It's much easier to launch a credential spearphishing attack than it is to launch something like a zero-day against a well-updated and maintained organization. Now, you might think, what about two-factor authentication? Right? And I think the community has done a terrific job with 2FA, but I think we need to acknowledge that there are sort of a number of challenges and hurdles before it's sort of seen in widespread adoption. Right? We all know there are cost problems, usability problems, so it has incomplete deployment. And so as a result, many 2FA solutions today are often still phishable. Right? If you use an app or a text message, the attacker can just ask for that 2FA code right after they phish your credentials. And so really, the state of the world today isn't terribly great. We have enterprises that basically need to rely on users to self-identify attacks and report them. If they use 2FA at all, they often use these phishable 2FA forms like the enterprise we worked with. And in the worst case, you realize that the credential spearphishing attack has occurred during a post-mortem forensics investigation where you've been breached and you trace the origins back to that spearphishing email. And so really, our work is focused on improving the state of affairs today. Right? We really want to build a practical, and I really mean truly practical, detection system that an enterprise's security team can use to detect these kinds of attacks. Right? And we're going to aim for two goals. Right? The first is that for it to be practical, we need to have an extremely low false positive burden. And our goal is going to target minutes per day. Right? Our alerts should take less than minutes per day for an analyst to process. And of course, we want to detect many attacks, and we want to significantly raise the bar. But we're not promising a silver bullet. Right? This is a detection system, and so our goal is really to highlight a practical path forward that will detect many attacks, have a low false positive burden, but we're by no means going to solve spearphishing. And so in our work, we had a terrific collaboration where we worked with members of the Lawrence Berkeley National Lab, which we refer to as LBL. And if you don't know what that is, LBL is a US national lab under the Department of Energy, and they have over 5,000 employees. So they're quite representative of a real-world, large-scale enterprise. And we leveraged a ton of data from them, all in anonymized form. And so I'll go into these in more details when I describe our features. But at a high level, we sort of have SMTP header information, URLs and emails, network traffic logs, and LDAP authentication logs. And we draw upon these in various forms to derive our features. Now, when I set out to do this work, I thought, this is going to be super easy. We have all this data. Surely we can throw them into some sort of machine learning algorithm, and now it's going to pop sort of our successful detector. But we're going to run into a number of key challenges, and I'm going to highlight two in particular that are closely related. The first is that we have an incredibly small set of labeled attack data. LBL keeps an incident database, and at the time of our work, there were less than 10 known successful credential spearphishing attacks. Now, this really emphasizes and underscores the second problem, which is the base rate challenge. But what I mean by that is that the base rate of benign emails is so overwhelmingly common with respect to attacks, right? In this data set across 4 years, there are 372 million emails. And if we have less than 10 known attacks, that basically means we have 372 million benign emails. And so this huge imbalance of tens and millions of benign events to sort of 1 or 2 malicious attacks, that's just going to overwhelm standard approaches. And intuitively, you can think of it like this. Even if our machine learning algorithm that we trained had a 99.9% accuracy, it generated over 372,000 false positives because benign events are so common. Okay? And so to overcome these key challenges, our work is going to sort of lean heavily on 2 key ideas. And let's dive into the first right now. When we set out to do this work, we sort of took a step back and we said, let's think about the structure of spearphishing attacks. And this led to a taxonomy that broke down successful attacks along 2 key stages. The first stage is what we call the lure stage. And the idea here is that for an attack to succeed, the email must convince the victim to perform some action. Right? If the victim doesn't perform an action, then the adversary doesn't get to execute some malicious event. Okay, so all successful attacks need this lure stage where they convince the victim to perform an action. Then once they've convinced the victim to perform this action, they need to leverage it by executing what we call the exploit stage. Right? And so they've got the victim to sort of perform some action. Now they're going to do the action. And the exploit stage can take a number of different forms. It could be installing malware on an enterprise network, revealing their credentials, or it could be this thing like wiring money to a fake corporate partner. Right? And the focus of our work, as I said earlier, is going to be on this exploit stage where they trick the victim into revealing their credentials. And so let's walk through a modern credential spearphishing attack through the lens of our taxonomy. I have an example of a spearphishing attack designed to steal Berkeley credentials. And if we sort of look at what it looks like in the lens of these 2 stages, if we look at the first stage, we have the lure stage. And lure often has 2 elements, right? On one hand, you'll have some compelling content like the email shows. If you can't read it, the gist of it is basically your account's been blocked. You need to go to this website to reset your password. Otherwise, you can't use the internet. So they have that catchy content. But they're also going to have what we call some sort of a trusted or authoritative identity. Right? The user that's receiving the email needs to believe that the person is trustworthy or has some compelling reason to follow them. And our features are really going to focus on this latter aspect of the lure, this notion of a somewhat suspicious identity that's designed to imbue a sense of trust into the email. So, for example, the attacker might forge an email address or a from line to claim they're from the Berkeley IT staff from this email address, or they might actually compromise an IT staff's account and send the email. Now, after this lure stage, the exploit stage for credential spearphishing attacks in modern times looks a lot like this. There's going to be an embedded link in the email that the victim's going to click on that'll lead them to some phishing website where they'll submit their credentials. And in this case, there's a link in the email. The displayed text shows that it's an auth.berkeley.edu, but the underlying hyperlink actually leads to some not berkeley.edu domain. And so now that we've seen a concrete example, let's sort of look more deeply at what these features look like. As I said earlier, our lure features are going to target this notion that there's a suspicious sender present, right? And that's this notion that the email is going to claim to be sent under some trusted or authoritative identity, but it's not actually that identity. And our paper defines 4 different impersonation classes or ways in which the sender could be crafted or sort of stolen to be some authoritative identity. And for the purpose of this talk, I don't have time to go through all 4 of them. We're going to focus on one particular interesting class of them, which we'll call the lateral attackers. And in a lateral spearphishing attack, what happens is that the lure is actually going to be the attacker's going to go and they're going to compromise some trusted entity's account. In particular, our paper is only going to focus on compromised corporate email addresses. And so after the attackers compromise this corporate account, they're going to use it to spearphish other employees. And this is a tricky one, right? Because there's no forged headers here. They're using a real account that's been breached to spearphish other users. And so the intuition for how we're going to derive features that characterize whether the sender is suspicious or not is that we're going to look at the employee that sent the email. We're going to look at when they logged in to send that email. And we're going to try and identify whether they logged in under suspicious circumstances. And so concretely, we're going to draw upon our LDAP logs, which is this historical record of authentications that occurred across all employees. And we're going to drive a few features. The first is just a Boolean feature. We're going to ask, when the employee sent this email, did they log in with a new IP address they've never used before? Now, if that's the case, we're going to take that new IP address that they logged in, and we're going to geolocate it to some city in the world. If it doesn't geolocate to some city, we have some tricks in the paper to use CIDR blocks or ASN mappings to sort of approximate that geocity. But just assume that that new IP address, it geolocates to some city in the world. we're going to count how many times has this sender previously logged in from an IP address in the city. Right? And the intuition here is how unusual is it based on this sender's past history to be logging in from the city. The final feature we're going to drive takes sort of a more global perspective of that. We're going to take the city that this IP address geolocates to, and we're going to count the number of other employees at the organization that have logged in from that city. Okay? And so those are a set of features that characterize sort of the lure of a lateral spearphishing attack. We're then going to augment this set of lure features with a set of exploit features. And the idea here is we're going to try and characterize whether a suspicious action occurred. And along the way, we're actually going to do a filtering step where we're going to take all these emails that we could alert on, these 317 million emails, and we're actually only going to generate alerts in real time if the the recipient clicked on a link that was embedded in the email. And we call clicks on these embedded URLs click-in email events, and I'll use this term later. And the intuition here is that emails themselves for spearphishing, they're not harmful, right? It's the actions that result from spearphishing attacks, from spearphishing emails that are harmful. And so we only need to alert on emails where actions occurred, right? And here, the action in credential spearphishing is clicking on some embedded link that leads you to a phishing website. Okay? So now if emails do have links that are clicked on by the recipient, we're going to extract features that describe whether clicking on that link is a potentially dangerous or suspicious action. And the way we do that is you clicked on this URL. We're going to take the fully qualified domain name, this is the host name of the URL, so that includes all its subdomains. And we're going to characterize whether it's suspicious for an employee to visit that. And we're going to do that with two features. Here we leverage the enterprise's network traffic logs. And what we're going to do is we have this fully qualified domain name of a clicked URL. And we're going to count the number of prior visits in historical network traffic that anyone has made to a URL on this fully qualified domain. Okay, so that's one feature. The second feature is temporal. We're going to look in our network traffic logs. We're going to see when was the first date that any employee visited a URL on this domain. Okay? And then we're going to count the number of days that elapsed between that first visit and when the email arrived at the enterprise's inbox. Okay? And so that's our set of exploit features. And so we have a small set of features, right? It's quite incredible. But we're going to see that we can compose a sort of small set of principled features to actually have quite good results. And so we have our lure features, we have our exploit features, we can combine them into a feature vector for all of our emails. Now, naturally, sort of how do we leverage these features for detection? And we looked at and tried sort of three standard approaches in sort of the detection toolbox, and they all had sort of significant shortcomings. The first approach we looked at was we built the detector using manual rules. And what I mean by that is we have our features, we pick thresholds for every feature value, and we sort of said if you're less than this value or greater than this value for feature 1, greater than this value for feature 2, et cetera, for all of our features, then you're a spearphishing attack. There are a couple problems, though, right? One is that how do we soundly choose these thresholds, right? There's no way for us to know what these threshold values ought to be. And even empirically, if we identify what values work at LBL, how do we know how they generalize or if they'll generalize to other organizations? So there's sort of fundamental soundness and generalizability problems with manual rules. Now, you might think, well, what about supervised machine learning? Everybody seems to be doing deep learning these days. Maybe we can throw a neural net. And this sort of really goes back to the two key challenges that I highlighted earlier in the talk, which is that we have a small set of labeled attacks. And we have this huge set of benign emails, right? Tens of millions of benign emails to sort of one or two attacks. And so ultimately, supervised ML techniques are going to fail because there's just far too much noise, and so this vast array of benign and diverse behavior, and so few sort of attacks to draw any meaningful generalizable signal from. So the final thing that we looked at and tried was let's lean on maybe the unsupervised learning techniques or anomaly detection. And there are a ton of different approaches that you could try and that we looked at. You might try clustering approaches. There are density-based approaches and a ton of others, like sort of one-class SVMs. But really, they all sort of have three common problems. Right? The first is that they all require hyperparameter tuning or they make parametric assumptions about the data. And if you're not a machine learning person, that's fine. The black box intuition of what this means is that machine learning algorithms, when you train them, they take as inputs things called hyperparameters. And these fundamentally affect what the machine learning algorithm does during training and your final output. And so they're fundamental to sort of choose. But really, they're chosen through more or less trial and error. We call it cross-validation, but you can think of it as trial and error, which is not a terribly great process. The second sort of thematic problem that we encountered is that standard techniques are often direction agnostic for anomaly detection. That is to say, if you have a feature value, if that feature value for an event is 3 standard deviations above the mean, the machine learning algorithm thinks that's just as anomalous as a value that's 3 standard deviations below the mean, right? But that's not the case for our features and probably other security features. Our features have a directionality to them. And so I'll illustrate that with a picture. You can think of one of the features that we had, which was this count of, an employee sent an email, they logged in from a new IP address. How many times has that employee logged in from an IP address that geolocated from that city? Right? And this feature has a directionality to them. That is, the greater the value, let's say the employee is logged in 100 times from that city, it's much more benign than if the employee has never logged in from that city before. And standard techniques don't naturally sort of incorporate that. The final problem that we had that was thematic across standard techniques is that they're often content to call an event anomalous or alert on it if it's just anomalous or extremely anomalous in one dimension. That means if one of its features is extremely anomalous, it'll generate an alert. And in fact, the way we designed our features, and maybe the way that other security problems design their features, is that there's a more complex and specific relation between the features. In our case, for most of the attacks, or most of our features, it's the case that an attack is characterized by every feature being anomalous. And so even if you have an event where one feature is extremely anomalous, we don't want you to alert on that, right? And so standard techniques are going to alert on points, let's say, that are circled in red, where one of their values is extremely anomalous, but the others aren't. And we don't want our detector to generate alerts for those cases, because really attacks are characterized by every feature being anomalous. And so we really sort of want our detector to only focus in on points that look like the ones in blue, that are anomalous in every dimension. And so what we ended up doing is we said, standard techniques, they're great, but they're not well suited for our use case. And so we introduced a super simple technique called DAS, which is an unsupervised learning technique, or anomaly detection technique, that overcomes these 3 challenges. And so how does DAS work? Well, it's pretty simple. The first sort of key idea, or sort of the underlying idea behind DAS, is that the bottleneck for detection in using a detector is really the analyst's time. And so as the first sort of class citizen, we're going to take as input a budget that the security team specifies, which says, how many alerts are we willing to process each day? Then, given the set of events and their features, we're going to assign what we call a suspicion score for every event. Once they're scored, we're just going to rank or sort them by their scores. And we're going to output the B most suspicious events for the security team, so the top B events. Right, so it's a very straightforward and simple process. And you might think, clearly sort of the meat of this is step 2. Right? How do we compute this score? Because everything else follows from that. And what's nice and sort of beautiful is that the score for DAS is incredibly simple. In fact, I'm going to fit it in one bullet point. Right, so we have an event X in our data set, and we want to compute its DAS score. The DAS score is simply a count of the number of other events in the data set that are as benign as X in every single dimension. So every feature value of this other event is more benign than X. Right? And you can sort of see why this works, right? Because larger scores mean that many other events are more benign than X in every single feature value. Right? If a lot of other events are more benign than X, X is more suspicious than many other events. To help you sort of digest that, I'll have some pictures. So it's a pretty simple made-up plot. Basically, we have a X feature value, a Y feature value. As the values get bigger, they're more benign. As they get smaller, they're more suspicious. And so if we look at the purple point in the center, let's call that event X, we see that it has a DAS score of 3. Right? Because if you look at the blue bounding box, that shows the events that are more benign than the purple point in every dimension. Okay? On the other hand, if we look at the point in the bottom right corner, that purple point, if we look at its blue bounding box, we see that there's only one point that's more benign in every dimension. A is more benign in the Y and X dimension. B, while it's more benign in the Y dimension, it's not more benign in the X dimension. So it doesn't increment the purple point score. Okay? And so that's DAS. That's DAS scoring at a high level. It's super simple. And so let's sort of see what that produces. So I don't really have time in the talk to go over our real-time detector architecture, but basically we have these 2 key elements. We have our DAS technique. We have the features we extracted that we input into DAS. We have some system tricks and glue to make that a real-time detector. You can sort of see the paper. But we ran this real-time detector over a data set, which is sort of 4 years worth of emails, 370 million, 372 million emails actually. And how did it do? Well, the first thing we did is we asked LBL's security team, what budget should we use, right? DAS takes a budget, what should that be? And they said, 10 alerts per day is great for us. That's a totally normal value. In fact, they told us, we on a typical day process, over 240 alerts. So 10 alerts more, that's going to be a drop in the bucket. So we said, great. We took our real-time detector, we used 10 alerts a day as the budget, and sort of how did it do? Well, it actually performs quite well. So we discovered that there were sort of 19 spearphishing attacks, that some of which succeeded in stealing credentials, other of which failed, but the user ended up clicking on the link and didn't go through with it. And so we talk about how we sort of derived ground truth for those 19 in the paper. But out of those 19 spearphishing attacks that succeeded and failed, we were able to detect 17 of them. So that's an 89% true positive rate. And what's really cool about this is that among the 17 attacks we detected, 2 of them were previously unknown. So they were previously undiscovered and unknown to LBL prior to our work. Right? So we're able to detect sort of these novel attacks, which is really cool. Now, I claimed earlier that classical anomaly detection techniques are not sort of well suited for a variety of reasons for this problem. And we empirically tested that. So we have a real-time detector. We have these features. We just replaced DAS with a standard anomaly detection technique. So using the exact same features, exact same data, the exact same budget of 10 alerts per day, we sort of replaced DAS with all these different techniques that are standard, so KD, KNN, all these standard anomaly detection techniques, and we said, how does the best performing classical technique do in our real-time detector if we use it? And it turns out they do quite poorly, right? The best performing one only detected 4 out of these 19 attacks using the same exact data, same exact features, same exact budget. And in fact, if we really wanted to use one of these classical techniques, we computed that sort of the best performing one would need at least 91 alerts per day to detect the same number of attacks as DAS. Right? So in other words, our technique DAS, it basically does an order of magnitude better in terms of sort of the alerts it generates to detect the same number of attacks. Now, I said, 10 alerts per day. The team at LBL said that's a drop in the bucket. But we sort of wanted to quantify that more concretely, right? How much time does 10 alerts a day actually cost? And so we had really a terrific collaboration with their security team. And I can't imagine anyone else doing this, but their security team actually manually investigated every alert that their detector generated. So we ran a real-time detector across 4 years worth of data, right? So that's something like 15,000 alerts that they manually processed. And they timed how long it took them to do that. And the results were kind of astonishing for us, right? They reported to us that the average rate for one analyst to process all alerts per day, so the average rate for one analyst was 24 alerts a minute, right? When we got this number, we said, maybe you forgot a 0 or a couple of zeros at this number when you reported it to us, because that's sort of a shocking speed. But what it means is that an entire month's worth of alerts can be processed by one analyst in under 15 minutes. So the time burden for our alerts is literally seconds per day, which is astonishing. And so we said, OK, if you didn't make a computation error, sort of what led to this blazing fast speed? And they said, well, it was actually kind of simple for us. When we triaged these alerts, we were able to look at the subject of an email, sort of visit the URL of the email, and look at the from line, or the sender, the purported sender, and quickly determine whether or not this was a candidate for plausible spearphishing or not. And to sort of give us a sense for what that meant, they gave us the subjects of some of these emails, but nothing else. They said, we had a lot of emails that looked like clickbait, like never lose your keys, Waldar purse again. And they said, that's not spearphishing. It's just not. And there were other sort of emails that are a bit trickier. They had these subjects like invitation to speak at some summit. But if you look at the URL, you look at the sender, it turns out to be some page that doesn't really ask for LBL's credentials. And so that's also not spearphishing. And so our alerts actually have this structure where there are a lot of false positives, but they're sort of very easy to process. So to wrap this up, our work presents a real-time detector for detecting credential spearphishing attacks in an enterprise setting. It's sort of truly practical. In fact, LBL has implemented a version of our detector. It has sort of a pretty great true positive rate. It detects many, many known attacks. And it's able to uncover attacks that were previously undiscovered. It has an extremely low false positive burden, right? Its percentage-wise is 0.004%, right? That's 10 alerts a day. And it can literally be processed in under minutes a day. And there are sort of two key ideas that led to these results. The first is that we're able to sort of study spearphishing attacks and sort of identify this structure in them, which is this lure and exploit sort of structure. And from this structure, we can sort of derive and develop principled features. And it's quite amazing, right? We only had basically 5 features, and those were enough to detect a ton of attacks at a very low burden. And the second sort of key idea that underlies this is this really simple technique called DAS for unsupervised anomaly detection. And we actually think that DAS could generalize well beyond spearphishing. In particular, if you're in a setting where you sort of have these needle-in-the-haystack security problems, where you have a small set of sort of curated and directional features, you don't have a lot of attacks, they're very uncommon in your data, give DAS a try. It might sort of work for you. It certainly did for spearphishing. And so with that, I'm happy to take any questions. Thank you so much for your time.
Thank you so much, Grant. I think it's easy to see why this was an award-winning paper. I think it represents some of the best qualities of a good USENIX paper, which is it has a strong focus on what the actual constraints are and the problem, and then focuses on those constraints to make it a practical solution. So thanks.
Thank you.
So could speakers please remember to say their name and affiliation?
Konstantin Beznosov, UBC. Good work, good talk. So my question is about cases when employees access their email from outside of the enterprise network. Usually they don't necessarily use VPN.
Yeah, so absolutely. I think I didn't have time to go into it, but our detector definitely has some limitations, and one of which is we have limited visibility, right? This is sort of a NIDS, it's a network-based detector, and so if we can't see employees' traffic and things like that, then it's going to be hard for us to detect. And so I think the ultimate solution for that is something like an endpoint agent, which sort of is able to see what employees are doing remotely and things like that.
Grant, can I add to that?
Sure.
Another solution that we've discussed with the lab is rewriting URLs and emails. So
yes,
if you click, it goes through the lab anyway.
Right. Mm-hmm.
Jeremy Epstein, National Science Foundation. There's a spearphisher in the audience here who's furiously recoding what they do. How long will it take them to get around your mechanisms, and how do you respond?
Definitely. It's sort of hard to quantify time-wise what it will take. I'll say that it certainly is possible to evade our detector. The goal of this was to sort of raise the bar for attacks. And to sort of, detection is an arm race. And you've seen our detector has a very small set of features. And that was really a constraint of we were working with heavily anonymized data. And so we're not leveraging content in the emails or on the landing web pages. And so certainly, an adversary can evade us. But we certainly have a lot of sort of future features in data that we could draw upon to sort of increase the robustness of our detector.
I have one more question. So you talked about the cost of false positives. What about the cost of false negatives? In your particular case, how much would it cost the company to miss a spearphishing attack?
I see. I don't think we were able to quantify that. So I'll say that we detected 17 out of 19. One of which that we missed was a failed attack. So the employee went to the Credential spearphishing page and they said, oh, I think this is phishing. I'm not going to click on that. So the cost there is 0. And we could actually detect that attack if we upped our budget to 15 alerts per day. The one that we missed is a bit trickier. And I think it was actually, it didn't cost too much because I think this spearphishing attack stole, I think their Dropbox credentials but didn't use them. What had happened in this attack was that a while ago, a bunch of hosting sites like Dropbox and Google Drive, they had this feature where you could host static HTML web pages on sort of the domains of Dropbox or Google Drive. And what that meant is that these sites had extremely high reputation, right? Because visiting Dropbox or Google Drive, that's a high reputation domain. And so we weren't able to detect that. Yeah.
Let me add, you might be asking something different, which is, were there further spearphishing attacks in our data that we didn't find for whatever reason? And there, the best we can do is this site has a well-run security team. They take their incident database very seriously. They discover things post facto. That's where all those detections came from. So that's the best confidence we can have is we know in general, historically, they run a tight ship. But that's it.
Right.
I'm Richard from RSA. I see the features you're building based on the counts, absolute numbers. So for different enterprises, the network size will be, dramatically different. So how you envision like to generalize this model, DAS method, to different sizes of organizations? Because you may see totally different counts.
Right. So DAS is completely data agnostic, right? There's sort of no dependency on the particular data that was used to train a detector, right? It really sort of takes the data that is in the enterprise. So if you have a smaller enterprise, their distribution of counts might be a little different. But sort of DAS is going to look at the underlying data that you give it. And so basically different enterprises will have different counts, but sort of within those data sets, the features will be relatively scaled. And so DAS just uses relative rankings in the data to do that. So there's no need to tune it for different organizations.
Thanks.
Hey, I'm Kevin from the University of Maryland. I thought that was really cool. Awesome work.
Yeah.
I just had a quick question about your feature detection, your feature choices. Specifically, it seems the features, from my understanding at least, the features chosen were waiting until after the user has already clicked the link, which from a enterprise security standpoint is like, well, the attack is already over and successful, right?
Well, so I guess
it's like a spam filter that waits until the user deletes the email to detect the spam.
Well, there are sort of two, I guess, different aspects. One is we have real-time alert generation. So when they click on the link, we can still see basically in real time that they're clicking on the link. And the other, sort of as Vern mentioned, is sort of we're working on future work where rather than sort of doing real-time detection, we actually go proactively in emails and we rewrite their URLs to sort of different sort of URLs, perhaps leading through an interstitial page on LBL that sort of blocks them for at least temporarily logging in, sort of letting an analyst process that and then sort of letting the user visit afterwards.
Got it. Very interesting.